Hello, friends. Welcome back to You Can Do TV. $7 million cubic meters of seabed dredged, caissons weighing 2,600 tons each, sunk into position, a terminal 700 meters, out into the Atlantic, on ground never meant to hold anything heavier than wet sand. The surface looks solid. Underneath, everything holding it up is invisible. The part of a port nobody photographs will make more sense than the cranes everyone films. Open on the cranes, because every camera does. A finished berth waits below, crane rails run straight across new pavement, and ship-to-shore cranes arrive like rolling towers ordered for the shoreline. They look impressive, but the ground sees them differently, as concentrated weight. Every container stack, yard crane, truck lane, rail, utility trench, and paving slab adds pressure to land that used to be coast. Viewers see concrete, markings, and clean terminal geometry. Engineers see load, settlement, drainage, and soil slowly squeezing water out under stress. Call it a modern terminal if you want. The ground still behaves like ground. Settlement starts with the first serious load, before the port even opens, not years later. The risk is already embedded in the schedule. The traffic crisis arrived first, and the soil inherited the consequence. Containers increased, vessels became larger, and simply adding machines could no longer solve the bottleneck. Expansion had to push the terminal seaward and create new operating land from the coast. That unlocked capacity, but it created the harder question: can reclaimed ground become strong enough for full port loads? The expansion includes a 550-meter breakwater, roughly 7 million cubic meters of dredging, a 16-meter draft access channel, reclaimed yards, and caissons weighing about 2,600 tons each. After that come pavements, utilities, power, inspection areas, and cranes reaching across massive container ships. Capacity gets the headlines. Settlement gets the hidden labor. Nobody celebrates compaction at the opening ceremony, but that is what keeps the new yard flat beneath stacked containers, rubber-tired equipment, trucks, and crane loads long after the ribbon is cut. That quiet work decides whether the surface stays usable under repeated daily loading. Time-lapse footage is misleading because it compresses marine construction into a neat trick with large machines. Crawlers move, land appears, pavement spreads, and a shoreline becomes a terminal in minutes. The critical work is exactly what the speed hides: seabed preparation, fill placement, compaction, drainage installation, quay edge fixing, and load path checks before heavy equipment arrives. Wet ground is not automatically strong ground. Trapped water must escape before the soil can carry design loads safely. So the first bottleneck is simple. A port is enormous weight placed on ground never designed to hold it, and the weight keeps growing. Next, we go below the waterline to see why engineers have to move the seafloor before a port can even exist. The next machine is not building the pier. It is attacking the seabed first. A cutter suction dredger lowers a rotating cutter head, breaks underwater material apart, and pumps the loosened slurry away through pipes. Natural seabeds almost never match the needs of modern shipping. They are too shallow, too soft, uneven, or silted. Large vessels need the bottom reshaped before arrival safely. Here, machines redraw the coastline, which sounds exaggerated until the surveys decide otherwise. Old groins can be removed, a port basin dredged to targets such as -8 meters, and a sandbar breakwater formed using natural sand transport plus heavy rock. In one coastal port project, about 200,000 tons of rock supported the breakwater, while geotextile tubes and revetment layers protected the shoreline behind it. The bottleneck is sediment balance. Too much material in the navigation channel blocks ships. Too little on the coast lets waves steal the shoreline. That is why dredging is not just scooping a hole underwater. Material must be cut, transported, placed, measured, and often corrected after currents begin editing the design. The sea does not care about drawings. Crews keep surveying because underwater conditions keep changing, and the difference between assumption and reality becomes expensive fast. The project is never finished until the new bottom is proven by repeated measurements after storms. Cutting the seabed solves only part of the problem. The removed sand often has to work somewhere else. Dredged material can be pumped through long pipelines, spread across low areas, and shaped by bulldozers into a protective surface. The goal is to rebuild elevation, slope, and buffer space so tides and waves do not remove the coast faster than the system can recover. Used well, the spoil becomes protection instead of waste hauled out of sight offshore. Then marine construction turns strange. Rock must be placed where nobody can stand. A fall pipe vessel receives stone from a bulk carrier, maintains its position with dynamic positioning, and lowers a pipe guided by sensors and an underwater vehicle. The rock is not thrown randomly over the side. It is placed with controlled accuracy to protect foundations, pipelines, or seabed structures from scour. Accuracy is the bottleneck. A placement error of only a few meters can leave edges exposed, increase current attack, and create erosion exactly where protection was supposed to exist. Survey crews verify each layer while the vessel continues working day and night. The system becomes a floating quarry, conveyor, survey platform, and precision rock placement machine at once. Precision matters because every layer must land where the design needs it, without burying nearby structures under rock that adds cost but not useful protection. That control keeps invisible marine work dependable when vessels arrive overhead years later. This wind farm footage still belongs in the port story because scour is the same enemy under a different structure. Around offshore monopiles, 92,000 tons of armor rock, sized roughly 9 to 18 inches, can be installed with a fall pipe vessel and side dump unit. Flowing water slowly strips seabed material away from the foundation, reducing support over time. The vessel loads stone, sails to the site, lowers the fall pipe, and places protection under instrument guidance through day and night operations. The same logic protects quay walls, piles, and turning basins, where propeller wash and currents attack exposed seabeds quickly. Protect the foundation at the beginning, or repairs become far harder and more expensive after the port is working. The seabed is finally in the right place. But one question remains: why does steel have to vanish underground before a port can rise above it? After dredging, the port still lacks a hard border. Soft seabed and reclaimed fill can spread unless a quay wall locks the edge in place. At Tama, huge caissons do that first job. Crews lift the concrete boxes on airbags, pull them by winch, roll them onto a semi-submersible barge, tow them out, then pump water inside so each unit sinks onto its prepared foundation. A caisson weighing about 2,600 tons becomes part of the buried edge. The visible terminal needs a hidden backbone before cranes, trucks, and containers can load the surface safely for decades without sliding. A side-clamp vibratory hammer on an excavator can pick up a pile, rotate it, tilt it, vibrate it into soil, then pull it back out if alignment fails. That matters at small waterfront edges where a full crane setup is slow. The goal is not spectacle. The goal is vertical steel reaching ground that can hold the future edge safely.
Move the same idea offshore and the difficulty jumps. A crane holds the pipe pile, a template fixes the spacing, and a vibratory hammer forces steel through water into the seabed. In the marina footage, 40-foot steel piles and 30-inch diameters show why this cannot be casual work. Crews test, drive, extract, correct, and drive again until the pile reaches the target depth and line. The viewer hears noise. The port needs a load path. Each pile turns soft marine ground into a point where a deck, wall, or berth can transfer weight without sliding toward open water under repeated heavy, working loads. Offshore piling shows why the steel must vanish before concrete can matter. A guide frame fixes the position, a steel casing is vibrated into the seabed, drilling removes the material inside. A reinforcement cage is lowered, and Tremie concrete fills the shaft underwater. The casing is temporary control for a permanent foundation. Without that control, soft ground, water, and misalignment would turn the future quay into a structure with no reliable grip below. When sheet piles alone are not strong enough, the hidden skeleton becomes heavier. A combi wall uses large pipe piles as the main bending members, then sheet piles fill the spaces between them. Guide frames set the line before the pipe piles are driven, and the smaller sheets close the retaining face. Ports need this because key edges take several forces at once. Reclaimed land pushing outward, vessels pressing sideways, cranes loading the deck, and waves disturbing tow. The pipe piles resist the big push. The sheets stop soil loss. Together, they turn a muddy shoreline into an industrial boundary. Long steel plates disappear, one by one. Each sheet locks into the previous sheet, a guide frame keeps the line straight, and a vibratory hammer reduces soil resistance so the steel can sink. Why use interlocking plates instead of a simple wall on top? Because the port edge must hold back wet soil from below, not just decorate the surface. Soil under a quay is heavy, saturated, and eager to escape toward the water when loaded by containers and cranes. A sheet pile wall creates a buried retaining line. The weak point is the lock between sheets. If one interlock opens, water can carry fine soil through the gap, leaving voids behind the wall. That is how a strong-looking pavement can later crack or settle. The steel disappears, but its alignment keeps the port face from slowly losing the ground it stands on. That hidden line must be checked constantly during installation too. Strength is no longer measured by noise. For quaywall work beside operating terminals, busy roads, buried utilities, or nearby buildings, vibration can create the very problem engineers are trying to avoid: ground movement. In those situations, contractors may choose a silent piler instead of an impact hammer. The machine grips previously installed sheet piles, uses them as reaction support, and presses the next pile into the ground with hydraulic force before walking itself forward along the wall. In stiff soil, crews may first use pre-drilling or water jetting to reduce resistance, but the principle stays the same: controlled force instead of repeated blows. Why does that matter? Existing pavements, pipelines, foundations, and structures may already depend on stable ground. Excessive vibration risks settlement, cracking, or costly repairs while construction is still underway. The challenge is not simply driving steel underground. It is installing a new retaining wall without disturbing the ground already supporting everything built beside it. A pressing machine gives the same act another kind of mechanical pressure. 4 sheets are lifted as a set, placed into the previous interlock, clamped and pressed in alternating 550mm increments. The machine is not trying to impress anyone with impact. It is trying to keep the wall straight while limiting vibration. That matters because a quay wall is a long chain of small connections. One leaning sheet makes the next sheet harder to lock, and a long retaining line can slowly inherit that error. Ports cannot afford a boundary that looks straight only from a distance. The steel must enter the ground in a line clean enough to retain soil, resist seepage, and support later deck work. The bottleneck is not only force, It is repeatable geometry, under pressure, sheet after sheet, until the waterfront has a continuous buried spine without leaking support later beneath cranes, trucks, and stacked containers above. Hydraulic jacked-in piling closes the sequence. Controlled force can be more useful than impact. Precast piles are clamped and pressed into the ground while resistance and penetration are monitored. That feedback tells crews whether the pile is meeting the bearing expected below. Noise and vibration drop, which matters beside roads, utilities, warehouses, and working berths. The point is not the machine type. The point is why foundations must disappear first. A port cannot trust the concrete surface until the loads have somewhere safe to go beneath it every single day. A flat concrete wall looks like the obvious answer to ocean waves. The ocean disagrees. A smooth surface bounces wave energy straight back. The reflected wave collides with the next and doubles the impact. The wall tears itself apart. Loose rock does the opposite. Each stone absorbs energy, breaks the wave into turbulence, and lets water drain through. That is why engineers pile boulders into a revetment, flexible armor that survives by moving slightly rather than standing rigid. At Borth, the crew unloads Charlie Rock by excavator, placing each boulder where the Irish Sea has been winning for centuries. The rocks are too heavy for trucks on public roads, so they travel the last mile by barge, which is also how castle builders move stone. Because some logistics problems never actually get solved, just motorized. At West Bay, the Sea Rock 1 barge delivers granite armor directly to the beach. Tugboats hold position while loaders push boulders off the deck into the shallows. Building a rock revetment is not throwing stones at a beach. It is engineering a slope the Atlantic cannot take apart. At West Bay, Dorset, sand gets trucked in first to create the working grade against the cliff. A geotextile membrane rolls out on top to stop fine material washing through the rock joints. Then excavators arrive, each fitted with a hydraulic rock grab, because you cannot scoop a 4-tone boulder. "38,000 tons of granite armor placed across the east and west beaches of one small English harbor, delivered entirely by barge because the local roads would have crumbled under the weight. Grab operators work to trimble GPS, so each stone lands within centimeters of design. Bulldozers then regrade the surface to restore the public beach. We have all walked past a rock wall on a beach and assumed somebody dumped gravel there. They did not. Every stone has a postcode. Sometimes the old armor fails, and the shoreline has to be rebuilt, in weather that does not care about the schedule. At a coastal leisure park, timber groans and rock revetment took storm damage beyond repair. The contractor demolished everything, imported 14,500 tons of fresh rock from Norway across the North Sea because the right granite does not exist locally at that volume. Geotextile down. Rock on top. Offshore, a dredging vessel pumps sand directly onto the beach through a floating pipeline to replace what the storms took. If you have visited an English seaside resort and thought the beach looked suspiciously well-maintained, there's a fair chance somebody put a lot of it there. In Qatar, the exact principle scales up. 2 excavators on a narrow spit place, 3 to 6 ton armor rocks into the sea. One by one, each boulder gets gripped and set, except each one weighs several tons, so the first placement had better be the right one. Not every revetment gets replaced with bigger rock. Some get removed entirely, and the reasoning is worth knowing. At Hailing Island, a 40-year-old timber revetment took storm damage in both 2019 and 2020 beyond repair. Rather than rebuild, the contractor stripped the 140-meter structure out. Excavators dug through sand, trucks hauled timber away, the beach regraded to a natural slope with geotextile underneath. A beach that reshapes itself under waves sometimes survives better than one locked behind a wall. Water dunin shows the Dutch approach to coastal reinforcement. Dump trucks cycle clay onto the dike in relays on a scale that makes many English beach projects look like gardening. And what happens when the problem is the water level itself? A sea lock is what you build when the ocean and the canal refuse to agree on a water level. At Terneuzen, the site had to be created from scratch. A hopper dredger pumps sand into cofferdam enclosures for the outer lockhead. Then the inner head, open water converted into dry land. Over weeks, excavators grading fill around the clock. By the time the ground was ready for concrete, the crew had built more land than most developers manage in a year. The lock gates are the part worth watching. Every single component too heavy for normal cranes and too precise for any guesswork. At Terneuzen, each gate leaf and guide wall section arrives as a prefabricated unit weighing hundreds of tons. A heavy lift barge positions alongside. The crane takes the load, swings it over the chamber, lowers it into a slot cast to accept it within millimeters. Why does a sea lock exist? The water on one side is tidal, the other is a controlled canal. The lock holds water at a set level, lets a ship in, adjusts to match the far side, opens the gate. If you have used a canal lock in a kayak, the principle is identical. This one handles ocean freighters, and the gates weigh more than your house. Tolerances on installation are single-digit millimeters, on a structure flexing under thousands of tons of pressure every cycle. Every lift is one chance the tide will not wait. The lock controls water. Most ports also have to build the land. The water leads too. Most ports start by creating ground that did not exist. Then an edge of the sea cannot eat. At Clump Point, the jetty goes up from open water. A barge carries the piling rig. Steel piles drive into the seabed. Steel piles drive into the seabed. Cross beams lock onto pile heads. Precast panels lower in and concrete binds it. The jetty is the coastline. A marina without a breakwater is a parking lot without walls. At Leisure, a curved breakwater extends seaward. Dump trucks tip rock off the crest. The excavator shapes the armor. The breakwater creates the calm. At Gibraltar, the small boats marina started with little more than open water and a rocky shoreline. Everything else had to be built. Steel sheet piles drove into the seabed to form quay walls. Formwork and rebar went up along the pile line. Concrete poured in for the permanent quay face. The marina floor got backfilled and compacted. Floating pontoons lowered into the enclosed water, anchored to piles that let them rise and fall with the tide. Service pedestals went onto each berth: power, water, lighting. The promenade above the quay wall got its final paving and finish. Every boat owner sees a marina as a place to park. The contractor sees it as a piece of ocean that had to be turned into a room, with walls, a floor, and plumbing. We have spent this video watching machines reshape coastlines. The boats tying up here have no idea how much happened before they arrived. And that is the point. Sometimes building a jetty means demolishing the old one first. Demolition on water is harder than it sounds. At Dover, the Dunkirk jetty was wire saw cut into blocks underwater. A heavy lift barge named Enoch grabbed each block from the water and deposited it on the bank for breakup. When the seawall protecting a railway collapses, the repair budget stops being optional. At Dover, a seawall subsided in December 2015, closing the adjacent railway line. The fix: deliver over 150,000 tons of rock by barge to armor a 700-meter stretch. Each barge carries 1,500 tons and can only discharge at daylight high tide. Total cost over £38 million. If your commute crossed a rail line beside the sea, this is the construction that kept it there. After steel and rock, the hidden problem is water trapped inside soft soil. Ports, airfields, roads, and reclaimed yards often sit on clay with low shear strength and low permeability. A prefabricated vertical drain gives that water a shorter escape path. Its plastic core carries flow upward, while the non-woven jacket filters clay particles so the drain does not clog. With stage loading above, consolidation can shrink from years to months. The bottleneck is time. The ground must settle before cranes arrive, or the pavement pays later through dips, cracks, and uneven container stacks years after opening under heavy traffic. The next invisible job is separating mud from water without spreading the mud somewhere worse. Dredged sediment is usually too wet to handle, too dirty to ignore, and too bulky to move efficiently. A geotextile tube turns that slurry into a controlled filtering process. Crews prepare a mixing area, connect pumps and pipes, lay the tube on a liner, and fill it with diluted sediment. Water escapes through the engineered fabric, while solids stay inside and consolidate into a denser cake. Why does that matter for ports? Channels lose depth as sediment accumulates, and every dredging campaign creates material that must be handled safely. The bottleneck is disposal space. If water can drain quickly, the remaining solids become smaller, cleaner to manage, and easier to reuse or remove. The quiet fabric does a job that would otherwise demand larger ponds, longer delays, and heavier hauling during a busy marine construction schedule near water. Here the lesson is simple. Remove water and the problem shrinks. 10,000 cubic meters of sludge can become a smaller, spadable volume for disposal or reuse later. A port also needs places for material that nobody wants to see again too soon. Dredging produces sediment, and if that sediment is fine, wet, or contaminated, dumping it loosely can create a new problem instead of solving the old one. A geotextile container gives crews a controlled cell. The ground is leveled. A liner can be placed below. The fabric container is unfolded. Inlet ports are aligned, and slurry is pumped inside. Then the strange part begins. The container fills, but it also drains. Water passes through the textile, while the solid fraction stays captured and slowly consolidates. Operators watch pressure and filling height because the fabric is carrying a temporary load before the sediment stiffens. The engineering value is filtration plus containment. Fine particles are held in one defined volume, and the released water can be collected or checked. In coastal works, these filled containers may become part of erosion control, shoreline improvement, or managed disposal areas. The hidden difficulty is that mud is not just mud. Grain size, organic content, contamination, water chemistry, and pumping rate can change how fast the bag drains and how stable it becomes. That is why the setup looks simple, but the controls matter. The bottleneck is turning wet, dredged material into something that can stay put. Without that step, a port can deepen its channel and still inherit a disposal headache on land. The viewer sees a giant fabric tube, yet engineers see storage, filtering, joinery, slope building, and risk control working in one device. After the ground is drained and the mud is contained, the next question is harder. Who keeps protecting the coast after construction leaves? Some systems become a visible skin. A cementitious geosynthetic mat can be unrolled, cut, welded, hydrated, and cured into a hard liner within about 24 hours, useful wherever water leakage would undermine slopes and channels. Waterfront slopes fail when water pressure builds behind them. A reinforced soil wall with gabion facing lets water drain, uses rock to absorb wave and current energy, and ties the backfill together with geogride. The critical detail is filtration. Soil must stay behind, while water escapes safely without dragging the slope with it. Ports borrow from slope protection because failure starts sideways. Rockfall mesh, anchors, and geosynthetics keep ground from moving. The goal is not stopping nature. It is controlling where it can move safely. Stopping the ground from moving is only the beginning. The harder question is how you keep it that way for decades. After hidden drainage, coastal protection brings a harder lesson. Every safe dike has a calendar. Space becomes the first constraint near houses, where a wider soil berm cannot fit. Sheet piles are pressed into the dike body to improve stability without shaking nearby homes. Vibration, settlement, and lateral movement are monitored because coastal safety cannot create damage. The piles are not continuous everywhere, reducing steel use and limiting groundwater effects while still strengthening weak zones. The finished steel disappears below the surface. Designed for a century of service. Designed for a century of service. A retaining wall enters when raising a dike with soil would make it too wide. Here, a roughly 220-meter wall adds height in a narrow corridor between industry and village. During extreme water, higher waves cannot pass as easily over the crest. The wall is bare concrete at first, then becomes part of the place. Engineers choose it only when space is exhausted. Maintenance now has another bottleneck. Coastal safety must get cleaner without delay. Electric machinery changes the construction site. Equipment arrives by water. Where possible, battery packs are charged at a central station, and machines receive power at night or during operator breaks. The gains are less noise, fewer local emissions, less vibration, and better conditions for operators and nearby residents. The challenges: planning energy like material. A diesel tank can be filled. Electric fleet logistics require charging windows, grid access, battery movement, and backup thinking. Future dike work will ask whether the design is safe and how cleanly it can be built. Even on the Hanswert Dike reinforcement project, storm season turns planning into survival discipline. From October to April, every excavation is judged against water level, wind force, and wind direction before work continues safely on site. February proves coastal protection advances in sections before any final surface appears on site. March adds layers. One zone receives stone, another is graded near homes, and rural sections are shaped with trucks, rollers, and drainage pipes. The work repeats because each dike segment has ground, access, water exposure, and neighborhood constraints. By May, the sequence becomes clearer. Sheet piles are pressed near the village. Clay layers shape the new profile, and sand packages expand rural sections. One project uses several methods because the dike passes through different worlds: houses, fields, roads, and exposed water. A single design would waste money or create risk. That is why progress looks uneven from above. June pushes the work from earth-moving into precision. Sand beds are leveled, reinforcement is tied, concrete is poured, and surfaces are finished, while nearby roads and access points keep changing. The dike becomes a construction corridor carrying safety, drainage, traffic, and neighborhood compromise at once. Even a traffic roundabout can enter the flood safety schedule when access has to be rebuilt without cutting off the community behind it. Summer progress proves the project is not one machine pass along the shore. Crews finish revetments, build access, shape parks, adjust drainage, and keep moving material. Coastal defense spreads into public space because water safety touches roads, recreation, utilities, and daily movement behind the dike. The line is social as much as technical. September and October show the site entering another stage. Surfaces are closed, asphalt and stone protection appear, and temporary construction begins turning into permanent defense for winter. Late 2024 is where repetition becomes evidence. Materials are reused, stones are reset, asphalt is applied, drainage and park areas are adjusted, and the work keeps moving across separate zones. The detail is sequence. A dike cannot be opened everywhere at once because each exposed section creates a temporary risk. Coastal infrastructure is assembled through many small closures, each reducing one future weak point while keeping the surrounding area functioning. For viewers, the repeated updates are the point. Safety is verified through progress, rather than spectacle alone. January makes the calendar visible. Winter does not pause the coastline, so the project keeps checking surfaces, access routes, drainage, and unfinished sections. The useful question is not whether the site looks complete today, it is whether enough protection exists before the next high water event arrives safely. February 2025 continues the slow conversion from worksite to defense. Crews refine slopes, close gaps, and keep logistics moving. The coast gives no credit for half-finished protection, so every temporary edge must still be managed before the next tide cycle. March and April expose the real scale of finishing. Roads, top layers, stone faces, green areas, and remaining construction zones all move together. The bottleneck is coordination. A dike must protect water safety while becoming usable land again for people living beside it. That transition often takes longer than the heavy earth moving, while contractors hand pieces back without reopening finished protection too. July and August show the last visible edges being cleaned up. Paths, slopes, roads, and surfaces are refined. Safety now has to look ordinary enough for residents to trust again after crews leave. After the coast is protected, cargo still has to escape the waterfront. A port upgrade is built on the work nobody notices. Girders, road decks, traffic routes, and heavy connections behind the quay. As construction ends, attention turns from ground stability to cargo flow. Containers lose value when trucks, bridges, and gates cannot move fast enough daily after vessels unload. Ports are expanding, automating and preparing for bigger ships, rising seas, and cleaner operations, all at the same time. Ports have always adapted to bigger ships. Is there a point where ships become too big for the ports chasing them? Thanks for watching. Some of the most interesting engineering on the planet happens far from the cameras. We try to bring it back. Subscribe and the next one finds you on its own.